Welcome, everyone. This is the second Engage AI webinar in what is a series of presentations addressing the role of artificial intelligence practices in international development. My name is Art Westneat. I'm a senior development economist with 40 years of experience working on a wide variety of African development issues. My PhD is in public policy and political science from Indiana University, and I will be your moderator. At the outset, please mute your Zoom mic, and at the end of the presentation, you can unmute it to ask questions. Please identify yourself when you ask your question. Please also note that this webinar is being recorded. Our presenter today is Dr. Ryan T. White. He is an assistant professor of mathematics at the Florida Institute of Technology. He will address the questions, what exactly is AI and how can we use it to achieve development goals? Dr. White has considerable expertise in machine learning and probability theory. He works with the private sector in algorithm development and data science. He has an active research agenda centered on stochastic analysis and related algorithmic behavior. He teaches machine learning, neural networks, probability, and statistics in both the undergraduate and graduate programs at the Florida Institute of Technology. Plus, he is an author of 2 forthcoming textbooks. Ladies and gentlemen, it is my great pleasure to introduce you to Dr. White.
Hello, so welcome. Our talk today is the goal is to define what AI is in a functional and both functional and accessible way, and discuss how these new technologies can be used to help achieve development goals. So first, just a little about myself. I'm an assistant professor of mathematical sciences at Florida Tech, the director of the Neural Transmissions Lab. So Florida Tech's a university in the Spice Coast. You can see our picture here with the rocket shooting from Canaveral. You can see it from the campus. On the right there is my lab. On the bottom, you can see some of our projects. We do lots of computer vision, natural language processing, synthetic data generation, and machine learning. And our projects span applications for space, for geosciences, for medicine and development. Some of my pictures here are a box we developed to track features of satellites and automatically plan flight paths to go fly to them and repair them, or refuel them, whatever we need to do. So again, I'm only a mathematician. I certainly don't have expertise in all these spaces, but the tools that have been developed and are still being developed in AI allow me to jump across these different fields, where I, again, of no means have giant educations in these spaces. I certainly consult with folks who do, but this is something that's distinct about AI. It allows us to bring common approaches to problems across disciplines. So, to take several steps back, I'd like to kind of talk about what a suitable definition for AI is. So this is a sort of standard definition you would see from an awful lot of organizations. It's from OECD's Science, Technology, and Innovation Outlook. So they define AI as the ability of machines and systems to acquire and apply knowledge and carry out intelligent behavior, which is a nice definition, but as a practitioner, it's not a useful thing to me. You see, in the definition, it even uses the word intelligence. So, I mean, I don't know what this means as a functional type person. So as a practitioner, I simplify it tremendously and just use a definition of AI that's been out for quite a while, and it's simply machines thinking and learning in some kind of way. May be human-like, may not be human-like, doesn't necessarily matter to me if it solves the problem that I'm trying to solve. So it's a very wide field, but what most people in this field are actually doing is what's traditionally called machine learning, which are particularly algorithms that learn from data in some kind of sense. Either there are a lot of different things that fall into this category. Several paradigms that exist are supervised learning, unsupervised learning, reinforcement learning. So with supervised learning, this means that you have lots of examples of things, and you have lots of outputs that you know that those inputs should map to, and you try to recreate that. With unsupervised learning, you don't even know the goal ahead of time for your algorithm. You just try to find patterns that are somehow useful. And it's a wide class of things that you can do within this. And so the primary driver of recent improvements in these spaces, the things that you see that are just incredible improvements in computers doing traditionally human tasks, like things involving vision or things involving language or speech. These are mostly made up of deep learning algorithms, which are, again, a subset of machine learning. And these are neural networks that are, at least initially, were based on how human brains process information. We'll find that they don't exactly work like humans, but they're very effective at what they do. And so sort of the general progression of these ideas, the early ideas of artificial intelligence started in really the 50s and 60s with folks literally trying to build models of brains. Turns out that, the way that they thought brains worked at that time wasn't really the full picture, but they developed these little bits of things that they could run in a computer, which running things in a computer was much more complicated in 1950, but they could automate some things here, and everyone got quite excited. They thought, well, we're building little tiny brains. All we need is more computers. We can scale them up, and it'll be just like a brain. Not quite true. So what really developed in 80s and 90s, people started taking computing and merging it with statistics, essentially. And that's what most of machine learning was. And then since about 2010, 2012, deep learning really took off and started improving the ability of computers to do so many different things, which I'll delve into a few of them. And where I wanted to start is with the old idea of an artificial neuron that came out from some researchers, McCulloch and Pitts are usually credited with this. First, a disclaimer: I'm a mathematician, not a biologist, so I'm going to explain in my simplistic way how a biological neuron works. If you can see on the left of the screen, a neuron is just a nerve cell that's what's in your nervous system, your brain, and generally seems to be how we process information in some kind of way. And so these neurons have these things called dendrites. They look like little roots. And what they do, they pick up on electrical impulses that might be caused by a stimulus. Like, so if you touch the table, it activates a nerve cell in your finger that somehow sends the information from neuron to neuron up your arm into your brain and for processing. So each nerve cell, neuron does something like it receives a signal. There's a nucleus here. Some chemical reaction happens here, or electrochemical, I should say. And then a signal is passed forward out of these so-called axon terminals. So these axons send out new messages and they attach to new neurons. So if you can imagine a pathway of these cells just linked, they're extremely tiny, but that's what's in your nerve system. They're linked together in that way. So in the 60s, Frank Rosenblatt developed what was called the perceptron, which was based on this kind of rudimentary interpretation of how neurons work. And he turned it into something he could run on a computer. He turned it into math, essentially. So these arrows are meant to represent dendrites. And these signals, X0, X1, X2, these are signals that the neuron picks up on. We'll assume they're numerical values. So the way that neurons wire themselves together, generally there's a stronger push of signals that satisfy certain criteria. So some of the thinking here is that, you know, certain passageways learn to behave in certain ways, and they emphasize different types of inputs differently. But anyway, these inputs go into the artificial version of a cell body. And well, what did they do? They said, well, we don't know what actually happens in a neuron, so we're just going to do a little math. And so basically they just add up all those signals and apply some function to it. They call it an activation function. And basically they say, you know, will this thing fire stuff forward or not? Or how strong of a signal should it fire forward? So that's how it works. And so what they started with were pretty rudimentary tasks, like sensory tasks. So I wanted to show, in terms of computers, what happens when you try to give a computer a picture. So on the left here, we have a relatively low quality picture of a handwritten digit of a 4. And you know, that's generally how a picture looks. It's a little pixelated just because it's not high quality. But when you start in a computer, it looks like, or at least when I look at it as a human, it looks like what we see on the left. And that inside the computer gets translated into math, into numbers again. And so here you see, this is an array of numbers on the right side. And what these numbers represent is how dark the pixel is at each pixel location. So each of these are, I think, 28 by 28 pixels, or that's the image size. So these numbers are 28 by 28. And you'll see most of them are zeros. This is where the pixels are white. And then the darker pixels are black, or have higher numbers because they're darker. So you see in the main outline of the 4, you see numbers that are close to like 250. It only goes up to 256. I'm sorry, 255. And then around the periphery, you see smaller numbers. And what this corresponds to is the gray levels that are not quite black. And so what they wanted to do in the old days was say, well, if I give this picture to my computer, can I train my computer to automatically tell me what this number is? Tell me if it's a 4, tell me it's a 6, tell me it's a 9, whatever. So the way that they did it, they took these perceptrons and they created what they called sensory units. So on the left here, you can see what is sort of meant to represent a picture. And each pixel, or each little region of the picture, would go to one of these association units. And these are kind of the inputs that we see. And then we have our summing unit. This is the perceptron. And then we'd give an activation. And in the old days, it would output a 0 or it would output a 1. So you could only ask it yes or no questions. So if you give it a picture of a 4, you could ask the computer, is this a 4 or is this not a 4? Outputs 1 if it's a 4, 0 if it's not. So how did you do this in the 60s? Well, on the right, you see Frank Rosenblatt with the Perceptron Mark I. He physically, what you can't see here is on his on the left of the picture, there were the inputs, and what they were just little squares, and they would shine different dark levels of light on them that would represent exactly this kind of picture. So he took a literal wire from each one, mapping to each of the association units, which in his day was just individual pieces of hardware he had to deal with. For us, it's much easier. So as you can see, this is incredibly complicated. For a very simple question of giving it a bad quality 4 and having the computer tell me if it's a 4 or not. So it was incredibly complicated. But what happened later on is that all of these things that required physically running wires became things that we could just put in computer memory, which is addressable. And so we can control the addresses algorithmically, which means that not only is this way less work, But we can stack more and more and more of these artificial neurons on top of each other. And so what developed from here were what they call deep neural networks. If you've heard the phrase deep learning, we're talking about neural networks that are quote unquote deep, meaning they have lots of layers of these neurons. So it's exactly the same idea. We just stack a lot of them on top of each other. And we have some outputs that we expect. So this was not really feasible back then because computing hardware was what it was. But as we've progressed through time, it's got much stronger. And I have some examples of that coming up. And what was special about these algorithms, what we learned over 40-year span of comparing them to traditional machine learning algorithms like linear regression or other types of things like that you may have seen, is that they have very high capacity for learning, because every little neuron you see here, each one has a connection, and each of those connections are weighted. So if you can turn all the dials and decide how the weighting should go, you can encode tremendous amounts of information in this kind of structure. And this is a tiny one. Modern neural networks have, some of the most recent ones have actually billions of parameters. Some of the ones I designed to run on spacecraft hardware actually has about 70 million. And that's me trying to run stuff on very weak computers. But anyway, based on that capacity, they benefit even more from large quantities of data. And if I can give you a much more recent picture of where some of this work was, they moved from these simple tasks like recognizing handwritten digits to recognizing pictures in general. So here, there was the ImageNet Large Scale Visual Recognition Challenge. And this was a challenge that the folks at the Stanford Vision Lab came up with. And what they did, they went out and collected 1.4 million pictures and labeled what's in each picture. And it actually had a tiered structure. So if you had a picture like on the right here with a husky, there are several categories that apply to this. 1, it's a husky. 2, it's a working dog. 3, it's a dog. 4, it's a canine. You can see this is kind of a tree structure. So all of these labels would apply to the husky. For the working dog, dog, canine, carnivore, and so on would apply. For placental, all of these plus mammal would apply, and so on. And then they had this for a lot of different categories. So also vehicles, as you can see on the bottom. But altogether, there were 1,000 different classes. So each picture had one of 1,000 things in it, or maybe multiple labels applied to it. And so what their challenge was, they challenged the computer science world to develop algorithms that can learn to take a picture input and automatically output the correct labels for it. So, scaling up from handwritten digits to real life pictures is tremendously harder, because in these real life pictures, even if you have a lot of pictures of huskies, as we see here on the right, these pictures are visually very, very, very different from each other. This one has a background of grass. This one has bushes in the background. This one's in snow. So somehow an algorithm needs to automatically take all of these pictures in this category and say, these are all huskies. And so, the thinking was, this is just a really challenging problem. Probably no one is going to be able to make huge performance, not going to really solve the problem, but it was just a hard problem for everyone to aim at. And a lot of the community agreed. And so they figured this would be, this would last us 20, 30 years, new benchmark for us to work on. It's a big data set. But that's not quite what happened. This is a graph of error rates on this ImageNet data set over time. And this is a recap in 2015, 6 years after the initial challenge went out. And so every year they had this challenge. There was a conference, and a lot of people created their algorithm and submitted it to them, and they tested it on a separate test data set that the no one's model had seen before. And so these numbers are the error rates on data that the models have never seen before. Some new pictures. So 2010, the first year, 28% error rate, which honestly to me is relatively impressive. That means we're getting nearly 3/4 of our pictures correct with an algorithm, even though they have this tremendous visual variation in them. 2011, pretty good improvement, went down to 25%. 2012, something weird happened. We went from 25% down to 16%. Pretty huge drop. And you can see after that, it precipitously drops to 11, 7, 6, and finally 3.6% error. I didn't mention the box on the one on the right. This is the human error rate. So by 2015, the computers were classifying these images with 3.6% error rates, which is actually better than humans. These folks on the right ran some experiments, and they just took a sample of people and said, here's all these pictures, tell me they said, here's all the pictures, here are all the possible labels, you tell me what's in the picture. And turns out humans at this stage underperform the machines. So what did they do? They declared the competition over and said, we solved this problem. We need something harder. They moved on. So I'll discuss shortly what exactly happened here that kind of accelerated this. But based on this performance, we saw just really explosive growth in human interest in AI because it was so good at these things. So in the academic world, it's always been pretty popular. This is data from 85 to 2018. And each of these graphs are the attendance levels at major conferences for AI. And so, I mean, even in 2000, there were 5,000 people showing up for some of these conferences, but these are largely academics, also quite a lot of industry folks. Some of the major presentations are often by, Google or Microsoft or other folks there. But you can see about 2010, really about 2013, when the performance really started exploding, the attendance at these conferences really exploded too. So there was a lot of academic interest, a lot of industry interest. This kind of is a measure of both of these. And then, looking at human interest, just based on Google, you can see, the number of people searching for AI grew pretty tremendously. I know there's no vertical value here, but Google Analytics doesn't actually provide the raw numbers, but they do a relative search volume. But you can see it jumps many levels in this same time period, a little bit time delayed from when the academics got excited about it and industry folks, but it definitely picked up. So next question is why did this happen? Why 2012 to now, last 10 years, what happened? And personally, I say there are three primary causes. One, hardware. Computers got way better in a lot of different ways, way cheaper as well. Data availability. By 2012, I think most large companies who had internet presences were able to start collecting just giant amounts of data because it became free to store it, basically. Relatively speaking. So the data availability exploded, and also lots of innovations in algorithm development. So just a few things here that are probably not surprises to anyone. Computing power got far cheaper. And so this graph shows from 1980 to 2010. I can assure you that from 2010 to now that this pattern continued. And what you'll see is each dot here represents the number of billions of computations you can do per second for $1 of computing power. 1980, so $1 would get you about 9 billion computations. It sounds large, but what you'll see is that this scale here, it's not linear, it's logarithmic. So this is demonstrating exponential growth. So by 2010, we could spend $1 to get let's see, 100 million billion operations. So from 9 to 100 million in 30 years. So what this means is that all these neural networks, all they do is some arithmetic under the hood, basically. It's some very cheap operations. So if you can do very many of them, you can make your models way bigger. Here's the price of storage space, $1 per storage space over time. So 1980 to 2010, we go from 1 gigabyte of storage costing a little over $100,000 to costing under 10 cents. Again, continued, maybe not exactly, but the pattern certainly continues to be cheaper and cheaper in the last 10 years. And not only that, just the volume of data that people collect, capture, copy, and consume in the world. This is the data volume in a unit called zettabytes, which I wasn't sure exactly what that number meant. So I Googled it and I learned that a zettabyte is this many bytes. A byte being one piece of information can be stored. And you can imagine my dilemma of preparing a talk and saying, well, now I got to pronounce this number. I don't know how to pronounce this number. So let's scale it down a little bit. So 1 zettabyte is, let's see, a trillion. This is hard to deal with. So just to get my head around it finally, it's about 4 billion MacBooks worth of storage. And so we can see the number of those stored on computers came from, in 2010, 2 of those, to 2022, about 97. And these are projections into the future based on growth. So you can store a huge amount of information in this, giant image data sets, giant text data sets, any kind of data set you want, really, and they all exist. And so to kind of bring this down to earth and not bring it down to earth at the same time in a way, I wanted to just do a quick comparison between the hardware available on the Apollo 11 spacecraft, or the mission Apollo 11 inside their spacecraft versus an iPhone, which obviously is not a strong computer to us. And so I did a little digging, found that an iPhone is about 100,000 times greater in processing power and about 1 million times greater in storage capacity than the computers there. So even the things that we carry around in our pockets are tremendously more powerful than a machine that was able to get us to the moon and back. So that, being on the space coast of Florida and, being occupied a lot doing space projects, this is the thing that kind of made it clear to me how much of growth there was. And beyond that, I showed you some neural network architectures, like a deep forward neural network, like right here in the middle top of the page. So that was, the initial model that folks were using. Everything else you see on the screen, aside from maybe 3 to 4 of these, are just new architectures that researchers have come up with that are good at different types of tasks. So for computer vision, people mostly use these convolutional networks, which take some inspiration of how human vision actually works to perform well there. Generative adversarial networks can generate synthetic data. So if you have a data set and you need more data that's similar to it, that'll create it for you. There's even websites out there where these things can generate synthetic pictures of people. They're not even real people, but they look really convincing. Recurrent networks are things that have sort of memory built into them. So if you're doing things that work over time, they're very good for like natural language processing or audio, where you need, like in text processing, you have to have, to understand what a sentence means, you need to understand probably the rest of the paragraph that came before it. So it's kind of a long string you have to understand in order to understand what a certain sentence means. Sometimes maybe there are pronouns that refer back to something in the past, or other things that you can capture. And all of the rest of these we can't go through all of these clearly, but they're all just different different types of neural networks that have been developed that are very good at different tasks. And I noticed here there are even a number that are missing. There are things called transformers that came out in 2018 that aren't even here. This is from the Asimov Institute from 2019. So these things are being developed tremendously quickly. It's very hard to keep up as a researcher, actually. But just do a lot of reading and see what other folks are doing so that we can, take the ideas of theirs that we like and implement it for our problems. But anyway, this is just a visual representation of all the development that's gone on just by folks, exploiting new hardware possibilities, new data possibilities, moving into different problems. Which brings me to one of the main goals of the talk, which is to talk about what AI can bring to the development world, and in particular, some of the things that Engage AI is trying to do in this space, along with a number of others that are making some pretty big strides here. So there are a number of challenges compared to other places. Data on the development or social factors in different countries is very prone to being incomplete or low resolution, or it may not even exist. So in countries where there isn't a lot of tech infrastructure, people aren't even capturing the data, but much less organizing it and making it usable for people. And if you look at things like the UN's Sustainable Development Goals, these are goals that span most countries in the world, and they span most social factors that are important to societies that folks have agreed on at the UN. Something like 180 countries signed on. But it's nice. It covers a lot of things, but a lot of countries don't have the resources to put those together, or don't have the will to put it together, or and even in the best case, this provides a very small snapshot. It gives you 1 year worth of data. At each year they give you something like, here's the infant mortality rate in Morocco in 2010. Here's the infant mortality rate in Morocco in 2011, and so on. So it's yearly, so you can't really zoom in very far. And if you're looking at things like economic factors that change really quickly, that data is very limited in what it can do. And then a lot of tools that exist. There's a whole phenomenon of what's called transfer learning, where you can go take a neural network that someone else trained, download it on your own computer, and fine tune it to work with the new data that you have. So a lot of times we saw some projects recently in Africa that were looking at internet radio and capturing the audio. And they're using that audio to try to extract things from it automatically to see, what the attitudes seem to be like in that country at the moment. But they were really hampered in that the natural language processing tools, speech processing tools that exist, they don't exist for languages like Darija in Morocco. They exist for English and French and Mandarin, but they don't exist for some of these other things. So this is another challenge, that there are some tools we just can't really use without giant effort. So in that case, they had to limit themselves to radio stations that were speaking in English or French. And other things, very basic, even more basic things like access to resources like electricity or computers, the internet, education can be limited and unreliable in some countries that aren't as affluent as others. And these things are prerequisites. We can't really do any of this without computers, as we saw. We're back to Rosenblatt's days of running wires between every pixel of a picture, which isn't scalable. But there are a lot of opportunities despite this. One, AI is very adept at finding complex patterns even when data is incomplete. People do it on purpose, actually. They make their data set worse so that the model that it can train is better at generalizing. So this is an example from a recent paper where you have a picture of a fox, then you want to train your model to say that's a fox. So the way these models will do, they'll intentionally hide parts of the image. And they say, okay, I'm going to throw this at my model. I'm going to hide, the snout of this fox, and I'm going to give the picture to my algorithm and see if it can still figure out the answer. And so basically you're giving it incomplete data and asking it to do a task. This idea is nice here because we have a problem with incomplete data. If we have most of the data, but some of it's missing on occasion, AI can work around that sometimes. So that's quite nice. AI can also exploit unstructured data. So you can have things like natural language, speech. A lot of people are scraping social media and finding current thoughts on things in certain countries. Mobile communications, photos, videos, pretty much any kind of data you can store in a computer, you can train AI to work on it, which is good because you can do mergers of maybe you don't have a big data set of Darija audio. You might have a lot of Darija text, a lot of text we can extract from social media of folks using the language of Darija. And if you have that, you can use that to train your models. And then you can pair that with some speech that you can gather. And so you can take these pieces of data that aren't entirely compatible and merge them together in some kind of way to still find useful patterns in it. Beyond that, there are many things happening now that lower the barrier to entry. We already discussed the decreased cost of computers, but beyond that, you can use cloud computing. You don't even have to have a giant computer. If you pay Google $10 a month, you can use their big computers. I mean, I'm running research labs partially on, my lab has one computer, and we're running 7-8 projects. But what we have access to cloud computing. We just buy access from Google. So, I don't have to make a big purchase to get into the game. There are things coming that are called low code AI. You don't have to actually write much code. So, and you can still kind of train these models. That's nice because, it reduces the amount of education you need to be able to deploy these things. And there's tremendous amounts of free online learning in this space. So if you have access if you have internet access, you can get this stuff generally for free. I mean, I teach these things myself, and I very frequently direct my students to free resources online. It says, hey, this idea we covered is a little bit complicated. Here's another video that's free. I think would help you guys understand it. Other things, AI does things people can't do. It can extract patterns that really aren't actually easily explainable. This is an example I like called neural style transfer, where you take a piece of art and you can take a picture and train a model that will extract the style of the art and apply it to whatever picture you want. So this is a picture of our little toy satellites that we have in the lab. So I took, Van Gogh's Starry Night, and you can see that it puts some very strong detail of that painting into this picture. You can see the similar brush strokes and stuff, but I don't know anything about art. I couldn't even explain what those patterns are, but I can train a model to extract them and apply them to something. So there are some superhuman capabilities here in very limited domains. This is monitors of the screen. The coloration and the brush strokes apply here. This is Kid Cudi's new album cover because my students thought it was cool, and we could transfer that style. So this little like speckled look and these curvy brush strokes and stuff, they apply to our picture. So not only can we learn useful patterns, we don't even have to understand them necessarily, but we can exploit them. So that's some opportunities here. And then I have some more specific use cases that sort of demonstrate what's been done in this space. This was a research project by Google Research Ghana that attempted to map literally all the buildings in Africa. How on earth could they do this? Well, you know, 5 years ago they could not do this. Absolutely not. But Google has satellite imagery. They have a ton of it. There are even like public satellite imagery, like there's one called Landsat. It takes pictures of the entire globe every 17 days. There are other ones that run, at the same time, but they're offset a little bit. So you end up with like 2 new images of every part of the world, every 17 days. So, every 9 days or so, we have a new picture just from, open source satellites. So the way they kind of justified the problem is said, well, building footprints, how many buildings are in different regions are useful for mapping and population estimation, urban planning, humanitarian response to disasters. This can be very valuable where there are infrequent censuses or a high prevalence of informal settlements or rapid change. So these are things that are just, as of 5 years ago, impossible to really measure in a useful way. But what they did, they took 11 million satellite images spanning the entire continent of Africa. These pictures here are from 2 data sets. Each dot represents a location where they have a satellite image. Not only an image, but a sequence of images through time. So you can see pretty much the whole continent is covered, with the exception of parts of the Sahara where I suspect there just aren't that many settlements. But anyway, that was all they could get. And so they had rural images, they had images of towns, they had urban images. And so what they do, they trained a model to locate all the buildings, extract them, count how many there are. So what you can do is, for a single region, you can measure, what's the new construction look like in this region? If it may be a place where there are no resources to go in and actually do some kind of useful census. So we can come from the sky and still find out useful information. Again, we really never could have done this without these types of tools. And it performs most likely better than humans. I don't think there's a real comparison here, but they found that it was very effective. Another thing that's being done, there's an organization called the UN Global Pulse. They do a lot of AI in the space. So they do a lot of Twitter analytics. So they, in real time, every 5 minutes or so, they go scrape all the new tweets around all the ones they can scrape. And this is automated. So they have tweets from 50 million users. They have some demographic information on them. They estimate that somehow from 193 countries. And what they try to do is, for sustainable development goals, they try to see which ones are people talking about around the world. And you can see, if you select a particular SDG, better job opportunities, you can see a heat map here of who's searching for that. The darker ones are countries where people are searching for that more. So you can see in Saudi and France and the US and Brazil, South Africa, you see a lot of people searching for better job opportunities recently. If you pick another thing, you'll find that people in this heat map will totally change, because more people are talking about different things in different countries. And there's no human in this loop. It's just a computer automatically extracting these things and looking at them. On the right, you can see, you can also extract by country and gender. So you can see in Jordan, the most commonly searched topics are about most commonly tweeted about topics in this space are about education. You can see women a little more interested in that than men. Better job opportunities come second, and so on, with more men searching that or tweeting about that. So this is pretty good. You can get a pulse of what people are talking about. So this is pretty useful to policymakers if they're going to figure out, what's really important to the folks in the country, at least the tweeting population of the country. And this brings me to kind of our last segment here, where I want to talk about some of the challenges that exist and some of the automation we've been trying to develop through Engage AI, with in collaboration with some other organizations. And in this space, there's a wide data landscape. There are lots of data sources, not all equally reliable, but they're all out there. So everyone has separate data. So OECD, the UN, IMF, WTO, certain private entities, lots of government agencies and ministries themselves, they all gather quite a lot of data. Most of them make that available to the public. But it's not all merged together. So if there's information from the IMF that you could merge with UN data and make, interesting predictions or ideas for what should be high in the priority list, it's hard to do that. It requires a lot of manually going around and grabbing data from different sources and putting it together. And, as someone who does AI stuff all the time, I will tell you, this is by far the most time consuming part of the work. It's the really the hardest part of the work. When I have student researchers, it's kind of a guided process. So what I find is that this is the place where even they have the most trouble. So, I jump in and do this work usually and let them do the cool AI training, but it's difficult. So that's a problem that is worth trying to solve. And so just to zoom in a little bit on what data looks like. So from the UN, the SDG indicators database, you can see here's what it looks like for each. There's a standardized data structure, which is very nice. It makes it easy for me to pull it out and turn it into a mathematical structure I can use. It's very well disaggregated. So you can see this is high school completion rate, but it's split into categories by sex, location, wealth quintile, education level of their parents. You can see, what percentage of students are, graduating high school based on their family's information, based on where they are fiscally in the country, their gender, and so on. So that's quite nice. The problem, and on the lower left here, you can see this is the availability of the data. So at worst, for one is Sustainable Development Goal 1, there's 45% of the data complete. This is 2000 to present. This is across all countries. And so you can see most of the others, there's a lot of data available. It's the problems though, the data is yearly, it's only national, it doesn't zoom in closer geographically. And there is quite a bit of missing data, although for a lot of countries, there's a lot there. Just to show you the difference, the World Bank has its own data catalog. It has some standardized structure, but they have a lot of different versions of their structures. So when you want to pull all that together, that adds to the work. And it comes in many data structures. This is just me sorting them into types of structure they have so that I could manually go write new code to clean up each one. So that's what a lot of the work looks like. And Engage AI, we're trying to reduce that barrier to cut that down. So we're working on a data platform with Dr. Westneat here, myself, my students, some other folks that are collaborating. And what we want to do is be able to sort of ingest this kind of diverse data, clean it up into a form that can be used for AI, and then make a way to query it usefully. And so what we have a data repository. We just throw all the data in there, clean it up, and we have some query tools we can search. You can tell this thing, give me all the data from Morocco about healthcare from years 2015 to 2016 from the UN or the World Bank, and it'll pull all of that information. And if you have that in that kind of nice structure, you can put it into mathematical structures that are easy to operate in with AI that can pull out insights, models, predictions. And again, so we're focusing on this sort of upstream part of the work that, in my experience, is the most time consuming and the hardest to deal with. And hopefully in the future, we'll allow others to just log into it and say, hey, go pull whatever you need for your analysis as well as using it ourselves with our collaborators. I think my slide got stuck. Oh no, that's the last one. Okay, that's the end of the slide. But that's where we're headed. We're trying to collaborate with some different folks in Morocco, in Jordan, just different places where we were able to meet some people and get moving there. And yeah, so if there's one major thing I would hope that folks can take away from this is that a lot of potential in using AI in this space, and there's every reason to try to catch up with what industry's been doing, what academia's been doing, because all the tools are there, and we need to make this as accessible to people as we can. Thank you.
So Dr. Ryan, is that your last slide?
It is.
All right. Well, thank you very much for that presentation on AI and machine learning. I was curious if you could, before we open this up to discussion, whether you could discuss a bit more about how do you train these systems to, what do you mean by training in this sense? I know what it means to train a child and an animal, but I don't know what it means to train a machine.
Well, you're in luck, 'cause it's not much different. We go to this example.
Well,
So,
I can't spank a machine, I guess.
well, true. Well, you can't. You actually.
Pull its plug,
So what
right?
we do, we give the computer a picture, for example, and just let's focus on this problem. We give it a picture, and we tell it what we want it to find. So we have this picture with all these buildings, and we want it to find this structure on the right. We want it to understand, what buildings are separate from each other, which ones are the same, and to draw outlines of them, figure out how big they are, and so on. And so what you do initially, you just don't tell the algorithm anything. You just give it, 1,000 of these pictures and 1,000 of answers that it's supposed to give, and say, okay, find me something. It's going to give you something totally useless. It's going to be totally wrong. But on the back end, what it does, it takes what the algorithm predicts and it compares it to what the answer was supposed to be. And then, if the answer is way off, it in human terms, it tells the algorithm, no, you're totally wrong. This is where you're wrong. This is how you're wrong. And what it does, there's an algorithm called backpropagation. And what it does, it goes back through the layers of the network and adjusts all the weightings that Frank Rosenblatt was doing by turning a literal dial to find the strength of the signal that goes through each wire. So those strengths are controllable. And so when you have that output and the algorithm can measure how exactly it's wrong, it tells it how to nudge all of these weights, all of these intensities. And then you let the algorithm try again, give it another 1,000 pictures. All right, try again. And then it's still going to be wrong, but it'll be a little bit better. And you say, well, okay, here's how you're wrong now. And then we flow back and just repeat the process. And so essentially you make it better and better over time by adjusting all of the errors that it's made in the past. So, this is how I deal with my students. Like, they say, how do you do this problem? It's like, don't ask me, try it. And then they try it, and fair enough, sometimes they're totally off. And I say, well, you're kind of close, but here's a couple of things that aren't quite right. Here's another one, try this one. They try it, and they're much closer. They might still be wrong. I say, well, okay, you're closer, but here's what's wrong. Then here's another one, try this one. And eventually they get it. They learn how to do it. So the computer, these algorithms largely operate the same way.
Okay. Well, let me open this up to a general discussion. Are there any questions among the participants? What you want to do is to open up your mic and identify yourself and ask your question. Are there any questions in the audience? Let's see. don't see any. All right, so let me ask you, Ryan, what I would like you to elaborate on further on one of the AI ML issues that excites you the most when it comes to these tools and their applications to development. What is the most promising? What is the most interesting thing for you in your work applying these tools to international development?
Right. So since I'm a mathematician, I'm going to start with a little bit of math, but I promise I won't go very long with it. So here we had all of these architectures that existed. And so these are all just different algorithms that do different things. They're all in the class of neural networks. And there's something that came out in 2018 called a transformer. It's a different architecture similar to these. But what it does, it really democratizes who can use these algorithms. And the way that it does it is that a very common one is called BERT. It's a language model. It stands for bidirectional encoding of something, whatever technical words. It's called BERT, and it's a language model from Google. And what they did, they took giant masses of text. They downloaded literally Wikipedia and had, I think, 50,000 novels as well. And what they did, they wanted to train a model to do language tasks without any help in the way that I've mentioned. So as I've mentioned, what's really difficult and what was hard about this problem actually was going in and labeling what the right answer was on all these pictures. So they had humans go through 100,000 pictures and draw little outlines of the houses. So all of this work with data preparation is, again, the core of the work of this stuff here. But these transformers avoid this. It just gives you data. It just gives the model data. And this has been extended to vision problems and other problems. But what it does, it takes a big block of text. So we have this, and it automatically creates its own problem for the model to work on. So rather than having any labels, it just takes the text and it hides like 50% of the words from itself. So for example, or not 50, about 15%. So you might take this paragraph and it would hide the word footprints, it would hide the word mapping, it would hide the word areas, it would hide the word where. And what they do, they train the model, fill in the blank. Well, we know the answer. We just hid it from the model. So the thing that's crazy is that it learns by itself without really any help. It's just all automated, and it drastically cuts down the amount of work to train the models. That's the one thing that's great about it. The other thing is that it is very powerful. It doesn't just learn how to solve one problem. It doesn't go in and say, I'm going to find whether this sentence is positive or negative in intent. It'll say, well, I just want to understand language. And so by doing this problem that we create for it, it learns to understand language in a very much deeper way. And what it allows you to do is to, although these models are trained on giant server farms like at Google or wherever, everyone can go download the model. And what you can do, you can download the model for your local computer that may be, $500 computer or something that doesn't require a lot of resources. And you can train it for your small task in a few hours. You you take their work and fine tune it to your problem. So one reason in development this can be important is that it just makes it so much easier for people to get into the game without big resources. It doesn't require all the labor of doing labeling, and it can do diverse tasks. With this BERT model, 3 hours of training on my laptop, and it can figure out if movie reviews are positive or negative with 80% accuracy. It can also find parts of speech in sentences that I give it. It can, one problem I'm actually doing in this domain is trying to automatically understand engineering requirements, which are natural language. But basically, we can do this all in a matter of hours. And so what people have been doing with this lately is I've mentioned the lack of models in certain languages for speech recognition or text processing. So people have started taking, well, okay, I have a model for Italian, and say Spanish is a related language. Let's take this model, all this work that somebody else already did, and let's transfer it over to work with Spanish. And so people have, similarly in our context, Arabic models exist, but for the Moroccan language, Darija, it doesn't, but they're closely related. So there's an opportunity to transfer learn over to a new language that brings this to more applications for very cheap, basically.
Sounds to me like you can make a game for high school students out of this. But this is you're very, very close to having students compete against their artificially intelligent computer systems and try to either associate with it or disassociate with it, trick it, collaborate with it. I don't know. Is anyone working on something like this, or am I just behind the times and it's already done?
Yeah, yeah, I mean, there are humans who just try to give pictures that'll trick a model, but in my class, I always use the example of doing sentiment analysis of movie reviews. So I take a movie review, the text of a movie review from, Rotten Tomatoes or wherever, whatever website reviews movies, and I already know the answer. I already know how positive it is, but I train a model to to interpret if things are positive or negative. So I intentionally try to show them you can trick these models if you're clever. So like if I write, oh, this is the best movie I've ever seen, and I feed it to the model, yeah, it figures out it's great. If I give the model a quote that says, this is my brother's favorite movie, but I hate it, it's totally tricked. It thinks it's a positive review. So it can be limited. And then there's a whole other area of adversarial AI where people train models that intentionally try to trick each other.
There you go.
And the point is to try to figure out, how can I sabotage this other model or whatever nefarious purpose I might have, or more commonly, it's how do I fool this model so that I know how to adjust my model to be able to deal with that. So in my class, I even challenge, or I'm planning to challenge students to train some models that try to trick each other, just to learn more about how it all operates.
Well, let's see. Are there any questions among the participants before we close up? I don't see any. So let's finish up. We spent an hour on our webinar today. I want to thank you all for joining us today, and of course Dr. Ryan for his presentation. I hope you will join us for the next webinar series in the Engage AI program. We'll be asking the question, where do we start with AI and development the next time we get together? So with that, I wish you all a good day, and hope to see you at the next session.
Thank you.
Thank you.